Hey everyone, we're the 2025 Airship project team, and thank you for tuning in to our presentation.
Hey, I'm Swayam.
I'm Rebecca.
I'm Amarachi.
I'm Gene.
I'm Oliver.
I'm Michael.
I'm James.
And I'm Adi. And over the past few weeks at SEAS, we've been working on a project that challenged us to think beyond Earth by designing an airship for Saturn's largest moon, Titan. However, in order to understand our solution, we must first understand our purpose.
Titan has caught the eye of scientists for nearly 400 years, but it wasn't until after the Cassini-Huygens mission that scientists discovered Titan was the only place besides Earth known to have clouds, rain, lakes, and seas of compounds like methane and ethane. This means that there's a potential for life on Titan, which could lie in the subsurface ocean or in the hydrocarbon liquid on the surface. Since then, scientists and engineers at Johns Hopkins APL have solidified our next mission to Titan, Dragonfly. Set to launch in 2028, Dragonfly is a rotorcraft that can travel aerially to a broader range of locations, allowing for more surface research on Titan as opposed to a traditional rover. Yet, long-term atmospheric data obtained from airships will provide crucial context for interpreting future Dragonfly data from the near surface. As Dr. Sarah Horst said, Titan is fundamentally different because the atmosphere and the surface are incredibly closely tied together.
High-altitude balloon platforms, like our prototype, can access infrared and ultraviolet wavelengths that ground instruments can't. From this, we can study absorption bands that can indicate molecule presences like water and carbon dioxide, crucial for identifying hydrated species, minerals, ices, and volatile organic compounds. Furthermore, Titan is especially well suited for airship-based exploration. Its atmosphere is about 1.5 times denser than Earth's, making it the most practical body in the solar system to conduct buoyant flight. Unlike rotors or aircraft, which require constant propulsion, airships can fly without using continuous energy. With Titan's atmosphere obstructing most solar energy, an airship model is especially beneficial as it allows for more power to be delegated to data collection and transmission.
With our project, we aim to design an airship to study environmental conditions analogous to Titan by collecting atmosphere data here on Earth. We did that by using temperature and pressure sensors, gas sensors, and a spectrometer for reflection spectroscopy. Using these sensors, we could conduct research that would complement the surface-focused goals of missions like Dragonfly by providing atmospheric context.
This calculation determines the maximum liftable mass for our airship in Earth's gravity. To calculate the budget, we start by finding the volume of the balloon, which is 0.44 cubic meters. Next, we plug in the values of Earth's standard air density and gravitational acceleration into the buoyant force equation and find a total force of 5.3 newtons. Finally, dividing that buoyant force by gravity gives us the maximum mass allowance of about half a kilogram. Because Titan has a much denser atmosphere and weaker gravity, it changes the mass budget to about 2.5 kilograms, about 4.5 times larger than the mass budget on Earth. Here we've calculated our propulsion force. On Earth, we have a thrust coefficient of 0.15, a propeller diameter of 7.5 centimeters, and a spin rate of about 883 revolutions per second. Next, with the thrust force equation, we calculate how much force the propellers can generate in each environment. Since we have two propellers, our results will be doubled. When calculated, the Earth-based propulsion force comes out to about 9 newtons, but Titan's denser atmosphere boosts that to over 40 newtons, showing significantly higher efficiency.
After making calculations for our design constraints, we set a list of engineering requirements to fulfill with our gondola design, such as the payload must weigh between 0.4 and 0.6 kilograms, and the balloon must lose less than 10% of its helium per day, and accordingly must maintain structural integrity in holding a stable flight for 10 minutes. This was accomplished by designing a novel O-ring clasp for the balloon seal, which achieved a helium loss of 5% per day.
We split our design into 3 focus categories: propulsion and control, gondola attachment, and sensor optimization. For control, we intended to minimize the number of propellers used in order to simplify wiring. At first, the propeller was put in the front of the gondola, with the 2 thrust propellers in the back. After catting the initial design, the vectoring motor was moved to the back with the other 2 propellers for aesthetics and increased torque. A stepper motor controls the orientation of the vectoring motor, allowing variable control over pitch and yaw.
However, when testing the pitch up and down control abilities, the airship largely translated vertically instead of rotating, due to the low torque relative to the airship's rotational inertia. While unintended, this feature was beneficial, as it allowed for more accurate movement. Yawing was also diminished, with the gondola simply translating left or right instead of actually rotating. For gondola attachment to the balloon, we initially considered a carriage structure, which would distribute the weight evenly across the balloon. However, due to weight and printing limitations, we settled upon using external strings. In our first flight, we attached these 3 strings to 6 separate hooks. Yet after testing, these hooks lacked the integrity to support the airship. Thus, in our final iteration, we decided to attach strings to clips, which would attach to the side of our modified propeller arm.
Our fully customized gondola design involved designing an aerodynamic yet sturdy structure that could integrate all of the electrical components. A simple boat design worked well for this. Screw holes were placed throughout the base for sensor mounts. 2 arms were placed to the sides of the gondola to optimize airflow to the propellers, ensuring maximum propulsion, and a recess was added to the back of the gondola to attach the stepper motor. Finally, we created a friction-sealed lid to cover the boat. One main constraint for the gondola design was mounting electronic components at clear vantage points, especially for external sensors. To remedy this, we created custom sensor mounts. For example, the spectrometer and external camera are mounted under the gondola to face the moon's surface. Our final design has a sleek and aerodynamic look. The arms were remade to increase propeller thrust and improve balancing. This was done by adding a bottleneck for a more stable connection to the ropes. To allow the lid to be easily removed and installed, 2 holes were added at the top for easy access. Ultimately, the final gondola weighs 0.47 kilograms, which fulfills our engineering requirement. To better understand the airship's performance and control characteristics on Earth and Titan, we created a computational fluid dynamics simulation. In our Earth model, we observed air hitting the front of the airship and slowing down, causing stagnation. As it traverses the side surfaces, the flow speeds up. However, towards the aft, we observed uncontrolled flow separation, creating uneven eddy vortices. In certain conditions, this can lead to unexpected drag and control loss. However, because the airship flies at low speeds and the helium provides strong enough inertial dampening, this behavior isn't expected to cause major issues in ground testing. Also, these vortices dissipate quickly in the model, so they shouldn't be of too much concern.
Next, we cloned the same simulation, yet modified the fluid we'd be using. Taking data from the Cassini-Huygens mission, we obtained air density, viscosity, specific heat, and compressibility values to input into the CFD model. This allowed us to model fluid flow if our airship was in fact on Titan. When the simulation was solved, it had a significantly higher Reynolds number, indicating greater turbulent flow overall. We observed this especially at the aft, where separated flow fails to restabilize, revealing stronger and longer-lasting eddy currents when compared to Earth. This creates a chaotic wake that could disrupt flight. To address this, future prototype and mission designs will require effective control surfaces to help manage and reduce this uncontrolled flow separation.
Here are our electronics and wiring components. The main controller is an Adafruit Feather Sense. It acts as a central microcontroller, communicating with multiple sensors, including an integrated sensor for temperature and pressure changes. For movement, the system uses 3 coreless brush motors. 2 work in parallel to move the ship forward and backward, while the third is linked to a bipolar stepper motor, which handles rotation. All motors are controlled using the Adafruit stepper plus DC motor feather wing, which acts as the motor driver for both brush and stepper motors. Power comes from a 3.7 volt lithium battery, regulated for the feather. A 5 volt power boost charger handles motor battery charging. Additional sensors include the air quality sensor and the Adafruit spectrometer for light and color analysis. A sandsail mini camera is used for visual capture, and an Adafruit multiplexer expands sensor connectivity. In our initial prototype, our airship contained a micro SD card to store all collected gas, spectral, and imaging data from sensors. However, due to card malfunctions, we instead collected the data directly through download. We made a fritzing schematic to map out the electronic and wiring design. This served as a baseline to recreate the diagram in real life and place the shown electronics inside of our gondola. To finalize our airship, we used a new Adafruit feather and feather wing and soldered header pins to connect. We also replaced our motors and resoldered their wires to stabilize the connection. A multiplexer was also added to connect the gas sensor. During development, we continually ran into conflicts with multiple sensors and electrical components requiring the same transmission channel on the featherboard. This was resolved by adding a multiplexer so that multiple sensors could connect to the same channel.
We also encountered difficulty with the stepper motor not making full rotations. We found that more torque was needed to rotate the stepper motor 90 degrees in both directions. To initialize the airship software, we set up a connection between the featherboard and the motors and initialized the onboard and external sensors. We used the Bluefruit Connect app to control our airship, which changed the motor throttle and stepper rotation using the button type and whether it was pressed or released. The directional buttons on the left control the back motor and the stepper motor, while the numbered buttons on the right control the motors on the side. Both the motor and sensor data were transmitted in real time as small packets over Bluetooth using NUS protocol to the Bluefruit Connect app. The sensor data was later exported as a CSV file for data analysis.
This is a video of our initial airship tests. We noticed that once forward motion has been established by the propellers, the airship continues to drift without a large decrease in speed, even after the motors have been turned off. However, we also noticed that the forward motion wasn't very stable, and there wasn't sufficient control of the airship's movement, as it tended to slowly drift and turn over time. In this video, we observed the airship's drift matching our CFD model. The turbulent flow destabilizes the airship, causing chaotic flight visible in the uncontrolled lateral drift. Our airship was equipped with scientific instruments to simulate advanced sensors used in Titan missions. We chose to find comparisons of our prototype sensors to more advanced mission technology. Instruments like the fiber optic gyroscope, known for high-precision orientation detection, and Huygens atmospheric structure instrument, collected detailed information about our pressure, temperature, and acceleration during descent. The mixed gas sensor on our airship mirrors the gas chromatograph mass spectrometer on Huygens, which identified nitrogen, methane, and isotopic ratios critical to understanding Titan's atmospheric history. Our spectrometer and external camera are also analogous to the visible and infrared mapping spectrometer on Cassini, which revealed surface composition and helped identify features like lakes, dunes, and ice.
Titan's atmosphere is made up of about 95% nitrogen and 5% methane. Even though the sun's radiation should be breaking down methane over time, the atmosphere remains questionably dense, suggesting the presence of a methane cycle, possibly due to surface features like cryovolcanoes, erupting water, and methane. On the left is Titan's temperature profile, showing well-defined atmospheric layers like Earth, but much more extended. At different altitudes, sunlight can trigger complex chemical reactions with carbon, hydrogen, nitrogen, and oxygen, forming organic molecules. These molecules can recombine into heavier hydrocarbons, which either join Titan's haze layers or fall to the surface, creating dunes and lakes. As mentioned earlier, spectrometers were widely used in the Cassini missions. The top images highlight important features captured from the missions, such as lakes, diverse terrains, and an image of the Salt crater, which displays exposed water ice. The spectral graphs below correspond to these features. The right graph reveals how methane lake depth affects reflectance, with deeper regions reflecting less light, allowing scientists to estimate lake bathymetry. The center graph displays strong indicators for different compounds, including water ice at 2.7 microns, and the left graph compares bright and dark regions on Titan, showing clear differences in absorption from 1 to 3 microns, likely due to reflective ice-rich areas versus darker light-absorbing dunes. If conducted on an airship, we can obtain readings with greater definition and clarity than existing data, allowing for a much more detailed understanding of Titan's chemical composition.
After iterating on our proof-of-concept airship design and researching it, we developed a hypothetical airship mission to Titan. Our main objective is to utilize the unique benefits of an airship model to fill in the scientific knowledge gaps of Titan. In this mission, the airship will enter at a 40-degree latitude angle, at an Earth-facing point for ideal communication. It would make a west to east pass according to Titan's eastward jet stream, while gradually traveling across wind currents toward Titan's north pole. We will time the airship's entry to Titan's winter season, since it provides the ideal north-south winds to allow the airship to reach the North Pole. During the first 5 months of our 10-month-long mission, the airship will circle Titan at an altitude of 10 kilometers in the troposphere. During this phase, it will use reflection spectroscopy to bounce light off Titan's clouds, collect temporal data, and capture high-resolution images of the surface and frozen lakes. Afterward, it will release a ballast and rise to the stratosphere, around 50 kilometers up, for another 5-month-long revolution. Here, the airship's focus shifts to atmospheric chemistry, characterizing Titan's hydrocarbon cycle and classifying upper atmosphere chemical compounds. Meridional wind oscillations, or north-south wind gusts, that occur during Titan's winter will help the airship cover more of Titan's surface. On our hypothetical mission, our airship's instruments aim to provide unique insights into Titan's surface and atmosphere that build on observations from previous missions and research questions. We would need to consider our airship's limited storage capabilities when flying on the outer planets and allow time to transmit data incrementally to minimize the risk of losing data in a malfunction or failure. Thus, for our mission profile, we varied the data collection periods of different instruments and sensors.
Our first instrument is called SCAN, which stands for Spectrometer Camera Atmospheric Notation. The spectrometer would work in tandem with the camera to collect spectral data from a variety of terrains. When the camera senses a new type of terrain, it would begin taking higher resolution images, and the spectrometer would transmit 5 readings, each about 0.2 seconds apart. This would be beneficial for observing molecules like methane, nitrogen gas, and water volatiles. Our second instrument is called GAS-O, which stands for Gathering Atmospheric Sensing Observations, and is composed of a gas sensor and an air intake system. For this instrument, we have two main objectives. The first objective is to map Titan's atmospheric chemical composition. We would quantify organic molecules such as C3H2, which have been detected in previous missions and are unique to Titan's atmosphere. Using this data, we aim to characterize Titan's hydrocarbon cycle. The second objective is to investigate gas distribution and variability across Titan by collecting atmospheric profile data every 20 seconds and looking for gas pockets or distribution anomalies similar to the Antarctic ozone hole on Earth. Also, we would monitor Titan's wind profiles by tracking how the airship drifts.
Finally, let's discuss our future research goals. First, as mentioned earlier, our current CFD models from Titan show significantly uncontrolled flow separation, which can impact stability and maneuverability on Titan. Adding active flow control surfaces like fins on a prototype will help manage separation-induced turbulence, improving overall flight performance for a future Titan mission. Second, instead of using a single inflated envelope, separate internal gas cells, or ballonets, will allow us to test an inflation mechanism of the airship as it arrives on Titan and provide greater structural integrity to withstand Titan's harsh cold and storms. The diagram above illustrates the ballonet layout and support structure we've been considering. Third, a simulated physics model of our airship operating under Titan-like conditions would enable us to test material behavior, stress distributions, and allow optimization of control algorithms well before building further physical prototypes. Such a model will allow us to better map and test an Earth-based prototype for future Titan use case. Fourth, due to Titan's approximately 1.4-hour communications delay, remote piloting is severely impractical. To address this, we plan to test a proportionally integral derivative, or PID controller, in the future to test autonomous piloting on an airship. This system will use real-time sensor feedback to autonomously adjust motor outputs, enabling self-correcting flight without human input.
Our main highlight of NASA Seas was the opportunities that we got outside of the project. We were given the opportunity to work on the ZQ, construct the ISS research proposal, converse with astronaut Dan Tanney, and learn more about flights in microgravity. These many opportunities illuminated the different career or research paths that we all could take. Seas, however, did not come without its challenges, as every intern had to adjust to a new environment while navigating newfound skills. Within our project, the High Altitude Balloon Project, we found it strenuous to analyze research about Titan to connect to a future mission. With the airship itself, we had issues wiring our sensors to our multiplexer while optimizing battery usage. These challenges, though, made us work harder and tested our critical and collaborative skills. Seas pushed us to adapt and thrive in a fast-paced environment, and ultimately to come out stronger.
My time at NASA Seas taught me that there are so many different ways to contribute to space research. I met an astronaut, a biologist leading a NASA lab, a flight director, and many like-minded peers with a variety of interests. I'm so grateful to Seas for helping me further my interest in space science and engineering.
Working alongside a team of passionate high schoolers who brought unique strengths to the table made every challenge feel like a shared opportunity to grow. Through late-night problem-solving, learning from our mistakes, and supporting each other, I not only gained valuable experience, but lasting friendships.
My time working in such a collaborative and dynamic team at Seas showed me that the value of a future career or education in engineering isn't defined by what is built per se, but by the people who it's built with. It was such a pleasure to be on this team, and it's certainly defined how I view a successful career.
At NASA Seas, I learned how our diverse skills can come together to create something none of us could do alone, building an airship in 2 weeks. I not only furthered my interest in engineering and research, but also made lasting friendships and connections.
At NASA Seas, working alongside motivated peers showed me the importance of dedication. Their drive inspired me to give my best in CAD and strengthened my passion for mechanical engineering.
At Seas, I was exposed to many opportunities in the STEM field. Being able to work with a group of such intellectual students allowed me to realize my potential within this field. I'm grateful for my experience at Seas, and I plan to continue pushing myself in future environments I surround myself in.
NASA Seas showed me the power of a focused team as we successfully built an airship, CAD, wiring, and programming included in under 2 weeks. It also started my passion for combining electrical engineering with programming to create innovative solutions.
Through Seas, I gained a broad perspective on the careers at NASA and met incredible peers and mentors who inspired and challenged me to continue pursuing aerospace engineering and also to have fun.
Thank you for watching!